Okay, today I'm going to be looking at this idea of internal energy and how we can relate that to thermodynamic values and processes. So first, let's have a think about the idea of internal energy. Now, a lot of the concepts of thermodynamics came from like when steam engines were being designed. So we can think of a lot of things in terms of a piston, a gas that's got molecules in a piston, and what's happening to the piston. Is there a force being exerted on this or not? So our internal energy in a system, which we call U, that's the letter we give it. So the internal energy U is a combination of the potential energy, PE, plus the kinetic energy. Now the potential energy, that comes from the forces between the molecules in our gas. So you can always think about potential energy to do with probably something you're more familiar with, which is gravitational potential energy. When you lift an object up, the further you lift it up, the more potential energy you're giving it, and the potential energy is coming from the attraction between that object and the Earth. So it's the same kind of thing. As we move these particles apart, we're increasing their potential energy because of the interaction between them. Now the kinetic energy, that comes from the vibration of particles and the movement of these particles. Remember, kinetic energy is kind of to do with the temperature. So temperature is a measure of kinetic energy. But these two things combined give us our internal energy U. And we know that U is always constant in a system on its own. If this piston is completely isolated, the energy cannot change. It has to remain a constant. Now when we look at a thermodynamic system and things like heat engines, what we want to know is what's happening, how much energy is going in or out of the system. And our kind of aim is to have an equation for the change in internal energy based on some quantities that we know. And those two quantities are going to be heat and work. So heat is something I've talked about in another video. So for more details, look at that one. Now heat is a transfer of energy when without involving any kind of force. So with no force. So this would be like putting a Bunsen burner under something. Okay, you're putting energy into the system, but you're not actually pushing. You're not exerting any kind of force. Work done is kind of the opposite. It's a transfer of energy but there is a force. So these are the two ways that we can get energy into or out of a system. And the question then is, how can we relate that to the internal energy? So let's have a think a bit about work done first. This is the first time we've met it in these videos. So let's imagine we've got a piston that starts out here. We've got our gas inside the piston, and a change takes place and the piston gets pushed out, so the gas expands, and this distance is delta x, and we know that the gas is pushing with a force of F. Now we know that work done, W, is force times the distance moved in the direction of the force. So F times delta x. Now when we look at gases, some common, if we think about the ideal gas equation, two quantities we use a lot are pressure and volume. So can we get this equation in terms of pressure and volume? So pressure, P, is force divided by area. Okay? So what I can say is, I can then I can do a little trick. So I do work done equals force divided by area times area. So these two areas would cancel out, times delta x. And so this equation is exactly the same as this equation. We've just added this a divided by a and times by a. The reason we do that is this. Force divided by area is pressure from this equation above, and then area times delta x. Our delta x is here, and it's multiplied by the area of this piston, and that is a change in volume. So it's delta V. So work done is pressure times the change in volume. And that's why when we have our pressure volume graphs, whenever we have a curve, the work done is the area under this curve, because it's pressure times the volume. Now you can do this, it's actually an integral, but for at this stage let's just look at it in this term. So now we've got these terms work and heat, which tell us about how energy is transferred. How do we relate these to the change in internal energy? So let's imagine we have our system, and we want to know what is the change in internal energy. So remember, delta is just a sign for change. And the way we do it, there's a convention in signs that we use. Now we always think about heat in this direction, where we're heating the system. So we're putting heat energy in, so that's positive. And we think of work as the other way. So we think of work as work done by the system. So that's negative. And that is our equation. So if you ever get stuck thinking about the signs, which sign you should be using, don't try and just memorize this equation. Think about what's going on. Draw the piston and think, I've got a certain energy in here and I want to know what the change is. If I've got heat coming in, if I put a Bunsen burner under this, then the heat is going to have a positive contribution. I'm putting it into the system. If it's the other way around, if this system is heating the outside, then the heat is coming away, so the heat would then need to be negative. With the work done, it's the other way around. If this system is expanding and pushing out on something, if it's pushing a force away, then that energy is leaving the system, so it's negative. But if I had this piston, if I was pushing on this piston, if I was compressing it, I'd be putting energy in which case it would be positive. So the trick to this is always draw it, try and figure out what's going on, and then you'll always be right with these signs. As always, if you've got any suggestions of what you want me to cover next, put it in the comments, and thank you for watching.